Welcome. So the topic we'll be discussing in this lecture is spread spectrum. Spread spectrum is a concept of spreading the bandwidth needed to transmit a data. The bandwidth of the signal will be spread. So why we do this? We do this basically to reduce the impact of narrow band interference. Let us try to understand how this concept works with an example. So this diagram shows the overall working of the spread spectrum. Here the first diagram, this is the original signal that we want to transmit. So this is otherwise called as user signal, which is represented in dark gray color. That is the one we want to transmit. And this signal, before transmitting, the user is spreading the signal across the frequency domain. Okay? The user is spreading the signal and then he is transmitting it. So during transmission, some interference were added to this signal. Two types of interference were added. One is the broadband interference, the other one is the narrowband interference. So the original signal is mixed with the broadband interference and narrowband interference, and this signal will be sent to the receiver. Now the receiver knows that the received signal not only has the actual data or the user signal, but it also includes the broadband interference and narrowband interference. So what the receiver will do in the sense, after receiving the receiver will extract the data, and the data is in the user signal, data in the sense the user signal is spreaded. Okay, that the receiver will convert it to a narrowband signal again. The spreaded user signal, the receiver will convert to a narrowband signal, something like this. Okay. But the received signal also has broadband interference. That the receiver will not do anything. The receiver will keep it as it is initially. Similarly, the received signal also has narrowband interference. That narrowband interference, the receiver will convert that to a broadband interference. Okay. So this is what the receiver will do initially at its end. Then the receiver will pass this signal through a band pass filter. A band pass filter is one which allows a range of frequencies. And using the band pass filter, the receiver will cut away. So the receiver will make sure that the band pass filter passes the signal that lies only within this frequency. That lies only within this frequency. So naturally, this extra broadband, the stretched out part, okay, the spreaded part, these all will be cutted away. Okay, so and now from this, so finally the receiver will have this kind of signal. Okay, so here if you see this signal, this one which is represented in dark gray, that has the higher power than any other signal. Then the signal which is represented in light gray, and then the white signal. Okay, so whichever the signal is having the higher power, from that the receiver will understand that that is the actual user signal. So this is how the signals are spreaded, and then it is transmitted to the receiver, and also it reduces the interference of the narrow band interference. Okay, now let us discuss two spread spectrum techniques. Okay, so first what we will be discussing is direct sequence spread spectrum. So we'll be discussing two types of spread spectrum. One is direct sequence spread spectrum, and the other one is frequency hopping spread spectrum. So first let us understand what is meant by direct sequence spread spectrum. So in a direct sequence spread spectrum, the actual will be having the original signal, the user signal that is to be transmitted, and that user signal, along the user signal will be XORed with a pseudo random number, which is a sequence of bits. which is a sequence of bits. Okay, so these bits can have any number, like it may be a 6-bit number or 8-bit number, or in some real-time applications it may be even as high as 128-bit number. Okay, but the basic concept is whatever the signal that the sender want to transmit, that signal will be XORed with a chipping sequence. This chipping sequence is basically a pseudo random number. It's a binary chipping sequence. Okay, as a result, whatever we get, that is the spreaded signal. That is considered as the spreaded signal. Okay, so here each user bit has a duration of TB. Duration in the sense the width of the clock pulse, the width of the clock pulse, and the chipping sequence consist of smaller pulses with a duration of TC. So the point is the clock pulse of the user bit will be larger than the clock pulse of the chipping sequence. Okay, so multiple chipping sequence will put together will be equal to one duration of the actual user bit. Okay, so the duration of user bit, that is the clock cycle, the clock pulse of a user bit duration will be larger, whereas the clock pulse of the chipping sequence will be much smaller. So multiple duration of chipping sequence put together will be equal to one duration of user bit. Okay, so the duration of user bit will be represented as TB, and the duration of chipping sequence, the duration of each bit of chipping sequence will be represented as TC. The duration of each bit of user signal will be represented as TB. Okay. So from this, what we can infer in the sense, the spreading factor will be equal to TB by TC. The spreading factor is given by the formula TB by TC. So where TB is the duration of uh, user bit and TC is the duration of chipping sequence. Okay, multiple bits of chipping sequence will be equal to the duration of one duration of user bit. Right? And the resulting signal's bandwidth can be calculated something like this. If the original signal's bandwidth is W, if the original signal's bandwidth is W, then the resulting signal's bandwidth will be S into W, where S is nothing but spreading factor. Okay, here spreading factor is represented as S, right? So, or this S is nothing but spreading factor. Okay, let me call it as SF, spreading factor. So if you multiply spreading factor into W, where W is the bandwidth of the original signal, if you multiply S into W, you will get the bandwidth of the resultant signal. So let us try to understand this concept with an example. So here is a simple example of direct sequence spread spectrum. So this is the original signal that we want to transmit. So you can see this original signal, its clock pulse is of larger duration. So this is the duration. So each bit's duration is TB, okay, which is of larger duration. Whereas this is the chipping sequence. Here we are considering this as the chipping sequence. 0 1 1 0 1 0 1 0 1 0 1 0 1. So this with this chipping sequence we want to transmit this data. So now if you see the each bit of chipping sequence, it is of very smaller duration. Each bit of chipping sequence is of very smaller duration. So if you see multiple chipping sequence will put together will be equal to one duration of the user data. So here 1, 2, 3, 4, 5, 6, 7. Okay. So that is 7 bits of chipping sequence is equal to 1 bit of user data. 7 bit of chipping sequence is equal to 1 bit of user data. So if you fit into that formula, then in that case, if Tc is equal to 1, okay, if Tc is nothing but the time duration of chipping sequence. If Tc is equal to 1, then Tb will be equal to 7. Tc is 1, then Tb will be 7, because 7 bits of chipping sequence is equal to 1 bit of user data. Okay, so then the chipping, then the spread factor S can be calculated as TB by TC. So what is TB? 7. 7 by TC, that is 1. Okay, which is nothing but 7. Okay, the spreading factor is 7. So here the spreading factor is 7. So one user data will be spreaded into 7 bits. That is the meaning. One user data will be spreaded into 7 bits. That's the meaning of this concept. Okay, fine. So let us try to understand how this logic works. So this is the user data, 0 and 1, that is what we want to transmit. And this is the chip sequence, 0, 11, 0, 1, 0, 1. Okay, so with this chipping sequence we want to transmit. Okay, so what you do is this 0 will be XORed with this particular thing. Okay, so this is 0, it means all zeros. So I mean the user data is all zeros, that is XORed with this particular chipping sequence. Okay, so XOR, what it will do, when the two inputs are different, it will create 1, otherwise it will create 0. Okay, so here 0 0 is 0, 0 1 is 1, 0 1 is 1, 0 0 0, 0 1 is 1, 0 0 is 0, 0 1 is 1. So this is the sequence that you are getting. Okay, for 0. Similarly for 1, what you are getting, all these things should be XORed with 1. 1 is nothing but all ones. Okay, so when you perform 0 1, it is 1, 1 1 is 0, 1 1 is 0, 0 1 is 1. Okay, and 1 1 is 0, 0 1 is 1, 1 1 is 0. So this is the resulting signal you are getting. The resulting signal is 0 1 1 0 1 0 1 1 0 0 1 0 1 0. So this is the resulting signal that you are getting, which is spreaded, because this signal is just this. Okay, this is spreaded, and this, here the spreading factor is 7. Okay, and this spreaded signal will be transmitted. This spreaded signal will be transmitted, and then it will be received by the receiver. Okay, so let us try to understand how this spreaded signal is transmitted and then how it is received by the receiver. So first the user data, it is applied to a chipping sequence. When you apply it to the chipping sequence, you get a signal which is the spread spectrum signal, because it is spread based on the chipping, based on the spreading factor. Okay, so the resultant signal is called as spread spectrum signal, and the spread spectrum signal is modulated with a carrier signal. Using a carrier wave, the spread spectrum signal is modulated. So once it is modulated, it will be converted to a high frequency signal, and this high frequency signal will be transmitted, over the wireless medium. Okay, and the transmitted high frequency signal will be received by some receiver. Okay, now the receiver first, what he does in the sense, receiver first perform demodulation. For performing demodulation, receiver should use the same carrier that is used by the sender for modulation. So using the same carrier frequency, the receiver demodulates the signal. So when he demodulates the signal, he will get the spread spectrum signal. Now we want to convert the spread spectrum signal to the user data. For that, this spread spectrum signal is passed to a unit along with the chipping sequence. Okay, along with the whatever the chipping sequence here used by the sender, along with the same chipping sequence, this this spread spectrum signal is paused. Okay. As a result, whatever you are getting, as a result, whatever the signal you are you are getting, so that is paused through a integrator. Okay, that is passed through a integrator. Integrator in the sense it adds up all the bits. It's as a result of whatever you are getting, that will be all the bits will be summed up. All the bits will be summed up. So these two units combined together is called as correlator. And then the signal will be passed to the final decision unit, which will convert this signal to the actual data. Will convert the signal to an actual data. Okay, so this is how direct sequence spread spectrum works. Okay. So the next kind of spread spectrum that we'll be discussing is frequency hopping spread spectrum. Okay. So with frequency hopping spread spectrum, what happens in the sense, the total available bandwidth will be split into many channels. Here the total available bandwidth will be split into many channels, and the transmitter and the receiver will stay in one of the channel for a specific time. The transmitter, the total bandwidth will be split into many channels, and then the transmitter and the receiver will stay in one of the channel for specific time, and then they hops in the sense, then they move into some other channel, then they will move into some other channel. So basically there are two types of frequency hopping spread spectrum that we'll be discussing. Okay, before that, the pattern of channel usage is called as hopping sequence. The pattern of channel usage is called as hopping sequence. That is the transmitter or the receiver, how long they stay in one frequency, and when they move from one frequency or one channel to another channel, that pattern of channel usage, pattern of changing from one frequency to another frequency, that is called as hopping sequence. Okay, and there is a terminology called dwell time, which represents the time spent on a channel with a certain frequency. That is how much time a particular sender or a receiver is spending on one particular frequency, on one particular frequency. So that measurement is called as dwell time. Okay. So there are two types of frequency hopping spread spectrum that we'll be discussing. One is slow hopping, the other one is fast hopping. So let us try to understand how this algorithm works. So first let us start with slow hopping. So with slow hopping, the transmitter uses one frequency for several bit period. Okay, the transmitter. So as we already discussed in frequency hopping spread spectrum, the bandwidth will be divided into multiple frequencies. Okay, so here the transmitter will be using only one frequency for several bit period. After a few bit periods, the transmitter will change the frequency. The transmitter will change the frequency. The advantage of slow hopping is it is cheaper, but the disadvantage is it is not immune to narrowband interference. It is not immune to narrowband interference. That is the disadvantage. And the next technique what we have is fast hopping. With fast hopping, the transmitter and the receiver will change the frequency several times during the transmission of a single bit. In slow hopping, the transmitter uses only one frequency for several bit period. Whereas in fast hopping, the transmitter changes frequency several times. Transmitter changes frequency several times during the transmission of a single bit. Just for transferring during the time required to transmit one bit, by the time itself the transmitter will change uh, several times in frequency. Okay. So fast hopping spread spectrum is actually a little complex to implement, and also here the receiver and the sender should be synchronized. The receiver and the sender should be perfectly synchronized. Okay? But the advantage of this technique is it overcomes the narrowband interference problem. It overcomes the narrowband interference problem to a larger extent. So let us try to understand frequency hopping spread spectrum with an example. So here we will be discussing two types of frequency hopping spread spectrum. One is slow hopping, the other one is uh, uh, fast hopping. Okay. So here in slow hopping, the user will stay in the same frequency for 3 data pulse. The transmitter will stay in the same frequency until the user transmit three pulse of data. After that, it will switch to some other frequency. Okay. So here this is the bandwidth. Here this is the bandwidth, and this bandwidth is divided into three frequencies: f1, f2, and f3. Okay. So the time duration of 1 bit of the user data is called as TB, and the time duration of the time duration of the hopping, the slow hopping or fast hopping, to represent 1 bit, that is called as TD. That is called as TD. Okay. So here initially the receiver or the transmitter and the receiver is using the frequency f2. So here the entire bandwidth is divided into three frequencies f1, f2, and f3. The transmitter is using the frequency f2 to represent a 0 or a 1. Okay. So, uh, so let us first try to understand slow hopping. So in slow hopping, here there is a 0, and it is not going to, so in this particular example, you can see from this diagram, it is not going to change the frequency until three pulses of uh, three pulses are over. Only when there is three, only when three pulses are over, it changes the frequency. Okay. So here we are assuming that initially it is working on frequency f2. It is working on frequency f2. Okay. So with f2, 0 will be represented like this, with a line below the f2 frequency, because it is 0, and 1 will be represented by a line above f2. Okay. And again 0 will be represented by a line below f2. So this is for this data. Okay. So like this the transmission continues, and after transmitting 3 bits, it is hopping it is hopping it is hopping from frequency f2 to frequency f3. Okay. Now the system hops from frequency f2 to f3. So here in f3, one is represented like this, and again one is represented like this. Okay. So this is about slow hopping. So in slow hopping, the frequency of the transmitter or the receiver uh, will not change until several clock pulses are over. Okay. So here you can see after one clock pulse how it works. Okay. So in this diagram, what we have discussed in the sense, three clock pulse is equal to one clock pulse of user data. And coming to narrow hopping, coming to fast hopping, here what happens in the sense, the transmitter or the receiver will hop multiple times uh, during during the transmission of 1 bit. Even during the transmission of a single bit, the transmitter and the receiver may hop multiple times. Okay. So here you can see, before for transmitting 0, initially the sender or the transmitter is using the frequency of 1 and is sending the signal 0. Again he is switching to f3. So here also, from here also he is sending 0. Again he is moving to f2, so from here also he is sending 0. Okay. So this is, and all this a change of hop, it occurs for just for one data of the one user data. Okay. And again You can see here the actually we want to transmit 1, so that is represented like this through f3, f2 and f1. Okay, so after f3 there is a line, so upper to f2 also there is a line, and after f1 also there is a line. So here also the concept is same. uh, that is the mm, that is the transmitter or the receiver hops from one frequency to another frequency, uh, uh, even during the time by which only one data can be transmitted by the sender, right? So again for transmitting 0, it is moving from f3 to f2 and then again to f3. Again for transmitting 1, it is moving from f1 to f2 and then again uh, f1. Okay, so this is how the concept of frequency hopping spread spectrum works. So let us try to understand how the modulation and demodulation part of frequency hopping spread spectrum. So first we have the user data. The user data is passed through the modulator and it get modulated. So once it gets modulated, what we have is the narrowband signal. What we have is a narrowband signal, and this and we keep this narrowband signal as it is. So before that, what we do is the hopping sequence is passed through the frequency synthesizer. The hopping sequence, whatever the hopping sequence is there, that is passed through the frequency synthesizer. Okay, as a result what we get in the sense, as a result we get the hopping, uh, as a result we will be getting the hopping pattern. As a result you will be getting the hopping pattern, and that will be, as a result what you get is a high frequency signal. So when you pass the hopping sequence through the frequency synthesizer, as a result what you get is a high frequency carrier signal, and that high frequency carrier signal will be used to modulate the narrowband signal, will be used to modulate the narrowband signal, and then it will be transmitted through the wireless media. And now the receiver will receive this signal, and first the receiver demodulates that using the frequency synthesizer with the same hopping sequence that is used by the sender. Okay, so 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 once he performs uh, hopping, once he get the particular hopping sequence, once he pass the hopping sequence to the frequency synthesizer, he will get the same carrier signal which is used by the sender, and this same carrier signal is used to modulate the signal that is received from the sender. Okay, so as a result again you get the narrowband signal. Again this narrowband signal is passed through the demodulator to get the actual data, to get the actual data. Okay, so this is how narrowband this is how frequency hopping spread spectrum works. So so what we have discussed in the sense, so in this particular lecture, what we have discussed in the sense, so first we have discussed about the concept of spread spectrum. So spread spectrum actually what it does in the sense, it spreads the signal across the frequency domain. So why we are discussing this concept? So basically we are discussing this uh, to reduce the narrowband interference. So initially we have discussed overall how the concept of spread spectrum works with these particular diagrams, and then we went on to discuss two types of spread spectrum. One is direct sequence spread spectrum, the other one is frequency hopping spread spectrum. So with direct sequence spectrum, what we do in the sense, we have a original user data and also we have a chipping sequence. Both will be XORed. As the result, what you get is called the resultant signal, and the resultant signal will be transmitted after modulation. And then the signal will be received by the receiver, and then it will demodulate, and then it will pass through the uh, integrator, and then the final decision will be made. So this is how direct sequence spread spectrum works. Coming to frequency sequence spread spectrum, so with frequencies sequence spread spectrum, the entire bandwidth will be split into many channels, and the transmitter and receiver will stay in one channel for a specific time and then it hops. So depending on how it hops, based on that we have two types of hopping. One is slow hopping and the other one is fast hopping. With slow hopping, the transmitter will stay in one particular frequency for three user data. With fast hopping, the transmitter will change will change the frequency frequently. Okay, the fast hopping is actually complex to implement because the transmitter and the receiver should be synchronized, but it overcomes the problem of narrowband interference. Overcomes the problem of narrowband interference. Whereas coming to slow hopping is cheap, but it is not immune to narrowband interference. So this diagram explains how the slow hopping and fast hopping works. So when you want to transmit one bit, the slow hopping will not change its frequency until three user bits are transmitted. Whereas fast hopping will change its frequency for one user bit transmission itself, it will change for three times. So as it is frequently changing the frequency, it is less prone to error, but it is a bit complex to implement. And then we have discussed uh, how this frequency, I mean, how these signals can be modulated and it will be sent and how it can be demodulated. So that's it about spread spectrum. Fine, let us stop here. Thank you.